The cosmos you see is only the surface of reality. We are about to journey through 30 mind-bending theories that propose our universe is not alone, but merely one thread in an infinite cosmic tapestry. By the end, you will possess a new understanding of what reality might truly be. We will explore if our universe is a hologram, a simulation, or one bubble in a frothing multiverse. What single question about existence would you want answered if you could know anything at all? The most popular answer to that profound question begins with a radical idea. Our universe might be just one page in an infinite cosmic library. This is the multiverse theory. It proposes that our entire cosmos, with its hundreds of billions of galaxies, is merely a single bubble in a vast, frothing sea of other universes. Each of these bubbles could have its own unique reality, born with a different set of physical laws. Some might have stronger gravity, making planets collapse instantly. Others might have no nuclear forces, so atoms could never form. The constants we take for granted, like the speed of light, could be completely different elsewhere. This concept arises from our best models of the universe's explosive birth, a period known as cosmic inflation. Scientists theorize that the vacuum of space possesses a strange energy that drives this expansion. In a scenario called eternal inflation, this process may never truly stop. Instead, it creates a forever expanding backdrop where new pocket universes constantly blink into existence, like bubbles forming in a pot of endlessly boiling water. Or picture a cosmic loaf of bread baking in an oven. Our universe is one air pocket inside that dough. As the loaf rises, more and more pockets form, each isolated from the others within the expanding bread. We are trapped inside our bubble, unable to see or touch the others, yet the greater multiverse teems with endless possibilities just beyond our perception. But the multiverse is not just a story of distant cosmic bubbles. It might be unfolding right here in every single moment through the bizarre rules of quantum mechanics. This is the many worlds interpretation, a theory proposed by physicist Hugh Everett III. It suggests that every time a quantum event occurs, the entire universe splits into multiple branches. Each branch is equally real, creating a constantly expanding tree of parallel realities. To understand this, we must revisit a famous, though unsettling, thought experiment. Picture a cat sealed inside a box with a deadly device. The device is triggered by a single radioactive atom. According to quantum rules, that atom exists in a blurred state of both decayed and not decayed until someone looks inside. In traditional thinking, the cat is both alive and dead at the same time, a paradox waiting to be resolved by observation. But the many worlds interpretation offers a stunning solution. The moment the box is opened, the universe does not choose one state. Instead, it splits in two. In one universe, you open the box and find a living cat relieved. In another parallel universe, an identical version of you opens the identical box and finds a dead cat horrified. Both events happened, both realities are real. This branching does not just happen for dramatic laboratory experiments. It happens constantly with every tiny quantum event. Every time an electron changes its position, every time a photon is reflected or absorbed, the fabric of reality divides. This means a version of reality exists where you took a different route to work this morning. Another universe exists where a single coin you flipped landed on the opposite side. The choices you make, and even the choices you did not make, are all playing out somewhere in the vast, branching tree of existence. The idea of branching realities is not the only way to find hidden worlds. Another theory, emerging from the deepest reaches of theoretical physics, suggests that parallel universes could be hovering right next to us, separated by a dimension we are utterly blind to. This is the concept of brane cosmology, a cornerstone of string theory. To grasp this, we need to rethink the very fabric of space. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings. For the mathematics of this theory to work, the universe requires more than the 3 spatial dimensions we experience. It needs as many as 10 or 11 dimensions in total. So where are all these extra dimensions? Brain cosmology offers a compelling answer. It suggests that our entire universe, all 3 dimensions of it, is actually a membrane, or a brain for short. Think of this brain as an immense 3-dimensional sheet, a vast cosmic tabletop upon which all the matter and forces of our reality are confined. This brain is not floating in nothingness, however. It exists within a higher dimensional space known as the bulk, and our brain is not necessarily alone. Countless other brains, each one a complete universe with its own unique physics, could be drifting through this bulk like leaves floating on the surface of a pond. The most mind-bending part is their proximity. One of these parallel universe brains could be mere millimeters away from our own, but that millimeter of separation is not across a distance we can see or travel. It exists in one of these curled-up, hidden spatial dimensions. To us, that other universe is completely invisible and unreachable, like a ghost ship sailing silently alongside our own. This leads to a profound question. If these brains are so isolated, how could we ever detect them? The answer might be gravity. In some models, gravity is the only force not completely trapped on our brain. It could be leaking or spilling between brains across the bulk. Imagine you are in a room with a wall you cannot see or touch. If someone on the other side of that wall pushes against it, you might feel a faint vibration. In a similar way, the gravitational pull from a nearby brain could subtly influence our own universe. Unexplained gravitational anomalies or strange patterns in the cosmic microwave background radiation could one day be the telltale vibrations from a neighboring reality, a silent neighbor brushing up against our own. Our universe might not be a one-time event, but a single heartbeat in an endless cosmic life. This is the cyclic model, a theory that replaces the singular Big Bang with an infinite series of cosmic cycles. Each cycle begins with a bang and ends with a crunch, only to rebound into a new beginning. Imagine the entire cosmos as a cosmic lung, breathing in and out for eternity. On the outward breath, space expands, galaxies fly apart, and the universe grows cold and dark over trillions of years. But then the breath reverses. A great contraction begins, pulling every galaxy, star, and atom back together in a cataclysmic event known as the Big Crunch. All matter and energy collapse into an unimaginably hot, dense point. Yet, according to this theory, that point does not vanish. It rebounds, it bounces. The immense forces of this contraction trigger a new Big Bang, forging a fresh universe from the ashes of the old one. This process repeats forever, an eternal rhythm of creation and destruction. In each new cycle, the fundamental laws of physics might be reset slightly. Perhaps the strength of gravity is a tiny fraction weaker, or the nuclear forces are a bit stronger. With every bounce, a new universe is born with its own unique properties, creating a multiverse not of separate bubbles but of successive generations. This elegant idea directly confronts one of cosmology's greatest mysteries. What happened before the Big Bang? The cyclic model provides a stunning answer. There was no before, because time itself is reborn with each new cycle. Our universe is just the latest iteration in an infinite chain, with no beginning and no end. But how could we ever find evidence for such a grand concept? The answer might be written in the oldest light we can see. During the violent bounce from contraction to expansion, unimaginable gravitational waves would have rippled through the fabric of space-time. These primordial ripples would have left a faint, specific imprint on the cosmic microwave background, the afterglow of our universe's own birth. Scientists are now searching for that signature, a ghostly pattern in the static that could be the ultimate fingerprint, proving our cosmos has lived many lives before this one. Yet another theory proposes that the solidity of our world is a grand deception. The holographic principle is one of the most radical ideas in all of physics. It suggests that our three-dimensional universe, with its vast galaxies, swirling planets, and our own tangible bodies, is not fundamentally real. Instead, it is a hologram, a magnificent projection from information stored on a distant, two-dimensional surface that surrounds us. All the richness of our reality, every sight and sound, could be encoded on a cosmic film that is fundamentally flat. This astonishing concept did not emerge from pure philosophy, but from the intense study of the most mysterious objects in the cosmos, black holes. When matter falls into a black hole, it seems to vanish forever, which presents a profound paradox. The laws of physics insist that information can never be truly destroyed. So where does the information about that matter go? The holographic principle provides a stunning answer. The information is not lost inside the black hole. It is perfectly preserved, painted onto the black hole's event horizon, the two-dimensional boundary from which nothing, not even light, can escape. The entire three-dimensional interior of the black hole is described by the quantum bits of information stored on its two-dimensional surface. Our universe, in a sense, might be like a giant black hole interior. We are living inside the projection. If this is true, then every event, every particle, and every force we experience is akin to a pixel on a cosmic screen. The resolution of our reality is so incredibly fine that we cannot perceive the pixels, just as you cannot see the individual dots on a high-definition television. This leads to a staggering implication for the multiverse. If our universe is a hologram projected from one surface, then other universes could be holograms projected from entirely different surfaces. The multiverse would not be a collection of floating bubbles or branching trees, but a vast library of cosmic DVDs, each one containing the complete code for an entire reality. Our deepest sense of being, our consciousness navigating a solid world, might simply be the experience of data being read and projected into existence. The universe is not just stranger than we imagine. It might be an illusion we are all collectively dreaming into being. If reality is a hologram, its true nature might be digital. The simulation hypothesis takes this one step further, proposing that our entire universe is not a fundamental reality, but an artificial construct, a sophisticated computer simulation running on the technology of a vastly advanced civilization. This is not science fiction, but a serious argument debated by philosophers and scientists. The core idea was famously formalized by philosopher Nick Bostrom in a paper titled, "Are You Living in a Simulation?" He laid out a logical trilemma, suggesting that at least one of three propositions must be true. First, almost all civilizations at our level of development go extinct before they can create advanced simulations. Second, any advanced civilization that could create such simulations would have no interest in doing so. Or third, we are almost certainly living in a computer simulation right now. If a civilization ever reaches the technological capability to simulate conscious beings, and if it has any desire to run such simulations, then the number of simulated minds would quickly and vastly outnumber the base reality minds. Statistically, you are far more likely to be one of the countless simulated beings than the rare original. The universe you perceive, from the farthest galaxy to the feeling of warmth on your skin, would be nothing more than data processed by an unfathomable computer. What might be the evidence for such a staggering idea? Some scientists point to the very fabric of spacetime itself. Just as a digital image appears smooth from a distance but reveals its pixelated nature when you zoom in, our reality might have a fundamental resolution limit. This limit is known as the Planck length, the smallest possible unit of space. You cannot divide reality into anything smaller than this scale. This pixelation of the cosmos could be the underlying code of the simulation, the finite processing power revealing itself. Similarly, quantum mechanics, with its strange, probabilistic rules where particles exist in multiple states until observed, behaves remarkably like a computer rendering system, only calculating the precise details of a scene when a user is looking at it. This saves on computational resources. If our universe is one simulation, then it stands to reason that our advanced creators could be running countless others, a multiverse of virtual worlds, each with different physical parameters, all existing within the memory of a single master computer. Your life, your memories, and the entire cosmic history could be an intricate narrative written in lines of code, a story playing out for an audience we can never see. This idea of branching realities leads to one of the most unsettling personal questions imaginable. What happens to your own consciousness when you die? The theory of quantum immortality pushes the many worlds interpretation to its ultimate, logical extreme. It suggests that from your own subjective point of view, you might never actually experience your own death. Your stream of awareness could, in theory, continue forever. Imagine you are in a situation that should be 100% fatal. Perhaps you are in an airplane that is crashing, or you are facing a firing squad. At the quantum level, the events leading to your death rely on countless particles interacting in specific ways. According to the many worlds view, for every possible outcome where a particle causes your death, there is another branching universe where that particle behaves just differently enough for you to survive. In the vast majority of universes, you die. But in a tiny, statistically improbable fraction of them, a miraculous sequence of events occurs. A vital component jams, a shooter's aim is minutely off, a structural flaw holds against impossible odds. Your conscious experience does not follow all the branches. It only follows the one where you continue to exist. From your perspective, you will always find yourself in a universe where you narrowly escape death, no matter how unlikely that escape may seem. You would simply experience a series of unbelievable survivals. This creates a deeply personal hidden universe for every conscious being, a unique timeline of experience that perpetually avoids the finality of death. The philosophical implications are staggering. It raises the question of whether consciousness itself is a force that navigates the branching tree of reality, always selecting the path of continued existence. This is not a theory about achieving immortality in a single world, but about your awareness perpetually shifting into a world where you are still alive. Of course, this leads to a strange and lonely existence. As you survive increasingly improbable events, you would watch everyone else's timelines diverge from your own. The world around you would become a stranger and stranger place, a reality sculpted by your continued survival against all odds. Your personal hidden universe would be one of increasing isolation, a testament to the bizarre and personal nature of a quantum reality. The very fabric of reality might be composed of numbers, not substance. This is the mathematical universe hypothesis, a theory proposed by physicist Max Tegmark that presents one of the most absolute forms of a hidden multiverse. It states that our physical reality is not merely described by mathematics, but that it is, at its most fundamental level, a mathematical structure. Think of a perfect triangle. It exists as a set of mathematical properties and relationships, independent of anyone drawing it on a page. Tegmark's radical idea is that such mathematical existence is the same thing as physical existence. If a structure is mathematically self-consistent, free from internal contradictions, then it is a real physical universe. Our cosmos, with its galaxies, stars, and the laws of physics, is just one specific, incredibly complex mathematical object. The force of gravity, the speed of light, and the charge of an electron are not arbitrary constants. They are the fixed parameters of the particular equation we happen to inhabit. This leads to an astonishing and all-encompassing vision of the multiverse. It is not just a collection of universes with slightly different physics. It is the set of all possible mathematical structures. Every conceivable universe that can be defined by a consistent set of mathematical rules must exist somewhere in this ultimate ensemble. There is a universe where space has 10 dimensions and another where time runs backwards. There is a reality governed by the simple geometry of a perfect sphere and another where the laws of chaos reign supreme. In this view, the reason our universe appears so finely tuned for life is not a miracle. It is a simple selection effect. We could only find ourselves within one of the rare mathematical structures that allows for the emergence of conscious observers to ask the question. The mathematical universe hypothesis removes the need for a creator or a fundamental substance. The multiverse simply is because mathematics is. Every story that can be written with the language of math is being told in a cosmos of its own, an infinite, silent library of pure logic where every book is a living, breathing world. There is a profound connection between the largest and smallest things we can conceive. Black holes, those terrifying cosmic vacuums, might not be the end of everything. They could be cosmic wombs. Black hole cosmology proposes that our entire universe exists within a black hole, and that every black hole we see is itself the seed for a new baby universe. This idea turns the cosmos into an infinite fractal, a reality within a reality forever nesting inward. To understand how this is possible, we must revisit the final moments of a dying star. When a massive star collapses under its own gravity, it squeezes all its immense mass into an infinitely dense point, a singularity. Traditional physics tells us this is the end, a point where the laws of nature break down. But some theories suggest a different fate. The incredible forces at the singularity might not lead to oblivion, but to a rebound, a cosmic bounce. The physics of this gravitational collapse could be so extreme that it warps the very nature of space and time, triggering a new Big Bang from the other side. Imagine it like this: a black hole forms in our universe. From our perspective, anything that crosses its event horizon is lost forever. But from the perspective of that infalling matter, it is not being destroyed. It is passing through a gateway. The singularity is not a final wall, but a tunnel that leads to an explosive new beginning. The matter and energy that fall in become the raw material for an entirely new space-time, expanding in its own set of dimensions, completely disconnected from our own. In this new universe, the black hole that gave it birth is perceived as the white-hot Big Bang, the origin of everything. This creates a breathtaking chain of creation. Our universe, by this logic, exists inside a black hole that formed in a parent universe. And every black hole that forms in our cosmos, from the supermassive ones at the centers of galaxies to the smaller stellar remnants, is currently gestating a new cosmos of its own. We are living inside one branch of an infinite cosmic tree, where each black hole is a bud ready to blossom into a whole new reality. The gravity that holds our galaxies together, the force that shapes our cosmos, is simply the pull of the parent universe's singularity, the umbilical cord connecting us to our cosmic origins. This theory offers a stunning answer to one of science's biggest questions. What sparked our Big Bang? The answer may be that it was the collapse of a star in a grander, older reality. We are not the first universe, and we will certainly not be the last. We are one link in an eternal chain of cosmic birth, a single leaf on an infinite tree of existence. The violent birth of our cosmos might not have been an explosion from nothing, but a shattering impact. The ekpyrotic universe model offers a radically different genesis story, one where our universe was forged in the collision of two cosmic giants. These giants are not planets or stars, but the same multidimensional brains we encountered earlier, vast sheets of reality drifting through a higher dimensional space. Imagine two immense, featureless sheets of glass, each one a complete universe floating silently in the dark. They are drawn together slowly, inevitably. When they finally meet, they do not pass through each other, they collide. That collision is our Big Bang. The immense kinetic energy of the impact is converted into the searing heat and frenetic matter that filled our infant cosmos, setting off the expansion we observe today. This is not a one-time event, it is part of an eternal cosmic cycle. After the collision, the two brains bounce apart, propelled by the force of the impact. The universe we inhabit expands and cools, just as it does in the Standard Model, allowing galaxies to form and life to emerge. But the story does not end in cold, eternal darkness. Over trillions of years, the brains are drawn together once more, setting the stage for another collision, another Big Bang, and the birth of a new universe from the ashes of the old. This creates a multiverse not of separate bubbles, but of sequential cosmic epochs, a series of universes each born from a titanic crash. How could we ever confirm such a dramatic origin? The answer may lie in the echoes of that primordial collision. Unlike the uniform expansion of cosmic inflation, a brain collision would have been a far more chaotic and directional event. This violence would have sent powerful, specific ripples through the fabric of space-time, gravitational waves that are fundamentally different from those predicted by other models. These waves would have left a unique, faint fingerprint on the oldest light in the universe, the cosmic microwave background. Our most sensitive telescopes are now hunting for this specific pattern in the static. Finding it would be like discovering the skid marks from a cosmic car crash, definitive proof that our universe began not with a solitary whisper, but with a shattering, multidimensional bang. Even within the branching pathways of the many worlds, another layer of creation might be unfolding. The daughter universe theory proposes that certain quantum events do not just split our timeline, but give birth to an entirely new cosmic structure, a separate and self-contained reality. While the many worlds interpretation describes a single, ever-dividing tree of possibilities, this idea suggests that some branches can snap off entirely, growing into their own independent trees with their own roots and futures. Think of it as the difference between a single oak tree sprouting a new limb versus a mature tree releasing a seed that grows into a completely new forest far away. In the many worlds view, all realities remain part of the same underlying quantum fabric, forever linked by their shared origin. But in the daughter universe model, a new universe is born wholly independent, with its own distinct space-time, its own beginning, and its own destiny, no longer connected to the parent that spawned it. This genesis could be triggered by the most profound quantum events, such as the collapse of a star into a black hole or a fluctuation in the energy fields of the early cosmos. At that moment of infinite possibility, the universe does not merely choose one path. It encapsulates one possibility into a new, stable reality and lets it go like a cosmic dandelion releasing a seed on the wind. That seed then inflates into its own vast cosmos, with its own galaxies, stars, and potentially its own observers wondering about their own origins. This means that every choice, every chance event might not just be creating a parallel version of our world, but could be responsible for the existence of entirely separate cosmic ecosystems, each one an island universe born from a quantum spark in our own. Our reality might have a perfect inverted twin. This is the mirror universe concept, a theory suggesting a cosmos where everything is a reflection of our own, from the spin of elementary particles to the very structure of life itself. This idea is rooted in a fundamental principle of physics known as symmetry. For a long time, physicists believed that the laws of nature were perfectly symmetrical, meaning they should work identically even if you viewed the universe in a mirror. This is called parity symmetry. In a mirror universe, your left hand would appear as your right hand. A corkscrew would twist in the opposite direction, and the very molecules that make up your body would have a reversed handedness, like a pair of gloves that are perfect mirror images. For decades, it was assumed this symmetry was unbreakable. Then, in the 1950s, two physicists, Tsung-Dao Lee and Chen-Ning Yong, proposed a shocking idea. They suggested that for the weak nuclear force, one of the four fundamental forces of nature, this mirror symmetry might actually be violated. Their experiments proved they were right, winning them a Nobel Prize. The weak force behaves differently in our universe than it would in a mirrored one. This discovery was monumental, but it also opened a fascinating door. If our universe prefers one-handedness, could an entire alternate universe exist that prefers the opposite? This mirror cosmos would be built on antimatter, the opposite counterpart to our normal matter. In such a place, an antimatter star could shine with antimatter light onto an antimatter planet, potentially hosting life forms made of antimatter. We would never see this universe directly, because if any of its matter touched ours, the two would annihilate each other in a flash of pure energy. They are forever separated by the fundamental asymmetry of the weak force. The only way we might sense its presence is through gravity, the one force that treats matter and antimatter equally. The collective gravitational pull from all the stars and galaxies in that mirrored reality would subtly tug on our own cosmos. Unexplained gravitational effects on the largest scales, effects we currently attribute to dark matter, could one day be traced back to the ghostly weight of a universe that is our perfect, untouchable reflection. The mirror universe is a place of perfect, untouchable symmetry, but our next theory confronts a cosmic asymmetry so profound it challenges our very existence. The Boltzmann brain paradox asks a deeply unsettling question. In a universe destined for maximum disorder, why does such intricate order, like you and me, exist at all? This thought experiment, born from 19th century physics, suggests that our structured reality might be the ultimate statistical fluke. If the cosmos is truly eternal or infinite, then even the most wildly improbable events are not just possible, they are inevitable. Given enough time, the random jostling of atoms in the void could spontaneously assemble a fully formed, self-aware brain. This brain would not develop through evolution or experience. It would simply pop into existence, complete with a lifetime of fabricated memories, convinced it is a person living in a real world thinking these very thoughts. The implications are staggering. Statistically, in a vast, cold, and mostly empty cosmos, such a random, isolated brain is astronomically more likely to form than an entire, ordered universe with billions of galaxies and a continuous evolutionary history. There are far more ways for a single conscious moment to fluctuate into being than for an entire 14 billion-year cosmic story to unfold. So, which scenario are we living through? Are you the product of a long, unbroken chain of cause and effect stretching back to the Big Bang? Or are you, right now, a lone Boltzmann brain, a momentary spark of awareness that just flickered into being in the endless dark, dreaming of a past that never was? This is not a question with a comfortable answer. If the theory is correct, then your senses, your memories, and your certainty that the world existed before this moment are all an elaborate illusion. The universe you think you know is a mirage, and you are its only fleeting inhabitant. The paradox forces us to confront the foundations of cosmology itself, searching for a reason why our complex, structured reality should be the norm, and not just a fleeting, lucky accident in an eternal sea of chaos. The unsettling possibility of being a fleeting brain in the void is not our only option. Another vision of eternity offers a more structured rebirth, an endless cosmic cycle of death and renewal on the grandest scale imaginable. Roger Penrose, the Nobel Prize-winning physicist, proposed a theory so beautiful and strange it seems almost poetic. Conformal cyclic cosmology suggests our universe is not the first, nor will it be the last. It is simply one aeon in an infinite chain of eons, each a universe in its own right, stretching from its own Big Bang to its own cold, empty end. The breathtaking twist is how these eons connect. It is not a violent crunch and bounce, but a serene and mathematical transformation. In the far, far future of our own eon, trillions upon trillions of years from now, the universe will have expanded into a featureless void. All matter will have decayed, black holes will have evaporated, and no structures will remain. there will be nothing left but a sea of massless particles and radiation drifting through an ever colder, ever larger space. In this state of ultimate dilution, the universe loses all sense of scale. A single photon wavelength stretched across the entire cosmos becomes indistinguishable from the cosmos itself. At this point, the geometry of spacetime can be mathematically rescaled, a process called conformal rescaling. This rescaling smoothly transforms the infinite, empty end of our eon into the hot, dense, ultra-small beginning of the next. The end becomes the beginning. The final whisper of one universe is reborn as the first cry of the next in an endless, seamless loop. But how could we ever find evidence for a universe that existed before our own Big Bang? Penrose made a stunning prediction. If our eon was preceded by another, then the evaporation of supermassive black holes from that previous eon would have left marks on our own cosmic birth. As those ancient black holes evaporated in the final moments of their universe, they would have released immense amounts of energy in the form of Hawking radiation. This energy would have been imprinted onto the next eon's starting point, our Big Bang. These imprints would appear in the cosmic microwave background, the afterglow of our own creation, as faint, circular patterns of slightly warmer temperature. Penrose calls these features Hawking points, and he claims to have found them in the data. These points are like gentle bruises on the skin of our cosmos, fingerprints left by the dying black holes of a forgotten reality. If confirmed, these faint rings in the static would be the ultimate souvenir, tangible proof that our universe is just one chapter in an infinite book, with the final sentence of every story serving as the opening line of the next. Perhaps the cosmos is not a place but a process. The theory that our universe is a quantum computer proposes that reality is not made of stuff but of computation. At the most fundamental level, the universe is not a collection of particles and forces, but a vast, ongoing quantum calculation. Space and time, the very stage upon which everything plays out, might not be fundamental. Instead, they could be emergent properties, a user interface generated by an underlying computational process happening at an unimaginably tiny scale. Think of the world on your computer screen. The desktop, the icons, the videos you watch, none of them are fundamentally real. They are a high-level representation, a convenient interface built upon countless ones and zeros being processed by the machine's hardware. In this view, our reality is the desktop. The three-dimensional space we move through and the time we feel passing are the intuitive interface. But beneath it all, the universe is running on a substrate of quantum bits or qubits. These qubits exist in a blurred state of multiple possibilities, and their interactions, their quantum logic gates, are what generate the laws of physics we observe. A particle's path is not a predetermined line, it is the result of a probability calculation. The force of gravity is not a mysterious pull, but an algorithm governing the relationship between informational entities. If this is true, it provides a startlingly elegant answer to why our universe appears quantized, why things come in discrete, indivisible packets. It is because reality is running on a finite, if astronomically large, amount of processing power. The Planck length, the smallest possible unit of space, is the pixel size of the cosmic screen. This leads to a breathtaking vision of a hidden computational multiverse. If our universe is one program, then other realities could be entirely different simulations running on the same cosmic hardware. Each one would be a separate process, a unique instance of a universe with its own initial conditions and physical laws, operating in a state of isolation we perceive as a different dimension or a parallel bubble. We are not just in a simulation, we are one simulation among countless others, all executing within the same ultimate quantum computer. Our inability to perceive these other programs is not a physical barrier, but a fundamental feature of the operating system, a strict separation to prevent one cosmic process from crashing another. The universe is not just stranger than we imagine, It might be the most complex computation ever performed, and we are the data, the processors, and the observers all at once. If a black hole is a cosmic drain from which nothing escapes, then its theoretical opposite would be a celestial fountain. This is the white hole hypothesis, a concept that is just as mathematically valid as its dark twin, yet we have never observed one. A white hole would be a region of space-time where matter and energy can only pour out, but nothing can ever enter. It would repel everything with an irresistible force, a brilliant and eternal explosion of existence. One of the most compelling theories suggests we have already witnessed the most spectacular white hole of all. The Big Bang itself, our universe's violent birth from an infinitely hot and dense point, perfectly matches the description of a white hole's output, a singular, one-way eruption of all space, time, and matter. This idea elegantly solves the puzzle of the Big Bang's origin. It was not an explosion in a pre-existing void, but the white hole in point of a gravitational collapse that occurred in another reality entirely. This leads to an even more profound connection, a possible architecture for the multiverse. Einstein's equations of general relativity allow for the existence of bridges connecting black holes to white holes. These are known as Einstein-Rosen bridges, though you likely know them by a more popular name, wormholes. Imagine a black hole in our universe, a one-way door into a cosmic tunnel. That tunnel, according to this theory, does not end in a crushing singularity. Instead, it opens out into a white hole, a gushing fountain of new matter and energy in a separate universe. Every black hole we see could be a gateway, an umbilical cord feeding a newborn cosmos. Our own universe, then, might be the white hole offspring of a massive star's collapse in a grander parent cosmos. And every black hole that forms here could be giving birth to its own baby universe right now, a vast branching tree of cosmic lineages. We are forever isolated from these parent and child realities, as crossing the event horizon of a black hole is a one-way trip from our perspective. Yet, through this hidden network of wormholes, the multiverse becomes an interconnected web, a silent ecosystem where the death of a star in one realm is the genesis of everything in another. Our universe might be resting on a foundation that is fundamentally unstable. This is the terrifying premise of the false vacuum decay theory, which suggests we exist in a state of precarious, temporary peace. The vacuum of space is not truly empty. It is filled with a background energy field, a kind of invisible fuel that drives the expansion of the cosmos. According to our best models, this field exists in what scientists call a false vacuum. It is not at its absolute lowest, most stable energy state. Imagine a ball resting in a small dip on the side of a vast, sloping mountain. It seems stable for now, but the true bottom of the valley lies far below. Our universe is that ball, sitting in its little hollow, believing it has found a permanent home. But at any moment, a quantum event could nudge it over the edge. Somewhere in the cosmos, in a random patch of space, a tiny bubble of true vacuum could spontaneously form. Inside this bubble, the laws of physics would be completely different. The fundamental constants that make our reality possible, like the strength of gravity or the mass of an electron, would be reset to new values. This bubble would then expand in all directions at the speed of light. There would be no warning. One moment, the universe would be as it is. The next, a wall of absolute transformation would be upon us, moving too fast to outrun or even perceive. From our perspective, it would be an instantaneous end. Every atom, every force, every structure in the universe would be rewritten according to the new, alien physics of the true vacuum. It would not be an explosion of fire and debris, but something far more absolute. It would be the erasure of reality as we know it, yet within this cosmic catastrophe lies a strange genesis. The space inside the bubble, now in its true vacuum state, would be a new universe with its own stable laws. The death of our cosmos would be the birth of another. This new reality would inflate and cool, perhaps giving rise to its own galaxies and life, completely unaware that it was born from the quantum demise of a world that came before. The trigger for this event is random, governed by quantum probability. It could happen tomorrow, or it could never happen in the lifetime of our universe. The unsettling truth is that the seed of our ultimate end could be germinating in the void right next to you at this very moment. The quantum world insists that a particle can be in two places at once, a superposition of states. But what if the particle is not the thing that is split? The many minds interpretation offers a startling answer. It proposes that the different possibilities in a quantum superposition do not create parallel worlds out in the cosmos. Instead, they correspond to different states of awareness within your own single, unbroken mind. In this view, the entire multiverse is not a sprawling external landscape, but a deeply internal, subjective phenomenon. Your consciousness is not a passive observer of quantum weirdness. It is the very mechanism that carves reality into separate, experiential streams. Imagine you are about to look at that infamous cat in the box. According to this theory, the universe does not split. The cat is not both alive and dead. There is only one box, one cat, and one physical reality. But your mind, in the moment of observation, does not settle on a single outcome. It branches internally. One stream of your awareness perceives a living cat, while another, completely separate stream of your awareness perceives a dead cat. Both experiences are equally real to the you that is having them, yet they are forever partitioned from one another. You are not aware of this branching as it happens. Each mental stream feels continuous and unique, with no memory of the other. Every conscious being is a universe unto itself, endlessly dividing with every glance, every thought, every quantum interaction. The hidden universes are not far away in another dimension. They are the private realities unfolding inside every conscious observer, a multiverse of the mind. This places consciousness at the very center of cosmic architecture, suggesting that the feeling of being a single self might be the grandest illusion of all. Our own cosmic neighborhood might be teeming with invisible citizens. This is the profound implication of supersymmetry, a cornerstone of modern theoretical physics. Supersymmetry, often called SUSY, is not just another particle theory. It proposes a fundamental and elegant partnership at the heart of reality, a deep symmetry between the two great families of particles that make up our universe. On one side are the fermions, the building blocks of matter like quarks and electrons. On the other are the bosons, the force carriers like photons and gluons. SUSY suggests that for every known fermion, there must be a superpartner boson, and for every known boson, a superpartner fermion. The electron would have a bosonic partner called the selectron. The quark would have the squark, the photon, a fermionic partner called the photino. This symmetry is so powerful it could solve some of physics' greatest puzzles, like the mysterious nature of dark matter. Yet, in all our experiments, we have never detected a single one of these superpartners. Where are they? The leading explanation is that supersymmetry is a broken symmetry. The superpartners are not missing. They are simply far, far heavier than their ordinary counterparts, so heavy that our most powerful particle colliders cannot yet create them. They exist at energy scales we have not yet accessed. This is where the concept of hidden sectors emerges. It is possible that the lightest of these supersymmetric particles, often called the neutralino, is completely stable and interacts with our familiar world only through gravity and the weak nuclear force. It feels no electromagnetic force, so light passes right through it. It feels no strong nuclear force, so it cannot bind to atomic nuclei. It is a ghost in the cosmic machine. Now take this idea to its ultimate conclusion. If one set of particles can form a hidden sector, why not many? Entire families of these shadow particles could exist, all interacting with each other through their own unique set of forces, yet completely oblivious to ours. They would form a shadow universe, a parallel reality made of shadow matter, occupying the exact same space as our own. You could be sitting in a chair made of these shadow particles right now, and you would never know. They would pass through your body, through the floor, through the entire Earth without a trace. The only way we might ever sense this hidden cosmos is through its collective gravitational pull, adding to the mystery we call dark matter. This means the emptiness of space is an illusion. The void is not void at all, but a bustling metropolis of overlapping realities, each one forever isolated from the other by the very laws that define them. The universe is not just expanding, it is layered, and we are only perceiving a single, thin slice of its true and crowded nature. If our universe seems finely tuned for life, that might be a cosmic coincidence. A more fundamental purpose could be driving its design. Lee Smolin proposed a theory of cosmic natural selection, where universes do not just exist, they reproduce and evolve. In this breathtaking vision, black holes are not merely cosmic tombs. They are cosmic wombs, the reproductive organs of the universe itself. The theory begins with a simple, powerful analogy. Just as in biological evolution, where organisms that are better adapted to their environment tend to have more offspring, universes that are better at producing black holes will spawn more descendant universes. Each new black hole could give birth to a new cosmos in its interior, a baby universe with its own set of physical laws. These laws would not be identical to the parents. During the violent rebound at the heart of a black hole singularity, the fundamental constants of nature might shift by a tiny, random amount. This is the cosmic equivalent of a genetic mutation. The strength of gravity, the mass of an electron, or the force binding atomic nuclei could all be slightly different in the new universe. Now, imagine this process playing out across an unimaginable span of time and countless generations. Which universes would come to dominate the multiverse family tree? The ones that are most prolific, the ones that produce the most black holes. Our universe, with its hundreds of billions of galaxies, each potentially harboring a supermassive black hole, and its countless stellar black holes, is a black hole factory of staggering efficiency. From this perspective, the laws of physics we observe are not fine-tuned for us. They are fine-tuned for stellar collapse and gravitational dominance. The very constants that allow for planets and people might simply be fortunate byproducts of a cosmos optimized for creating as many black holes as possible. We are not the purpose of the universe. We are living in a universe that is exceptionally good at replicating itself, a successful branch on an infinite, growing tree of cosmic life where survival is measured not in years, but in the number of new realities spawned. The solid world around you might be the grandest illusion of all. If the holographic principle holds true, then our three-dimensional cosmos is merely a projection, a magnificent hologram beamed from a flat, two-dimensional surface at the edge of our perception. This is not just a metaphor for our universe alone. It paves the way for a staggering new vision of the multiverse, an ecology of interacting holographic realities. Each universe could be its own distinct hologram, projected from its own unique cosmic film. The source code for our entire existence, every galaxy, every human life, every law of physics, would be perfectly encoded on our distant boundary. Another universe would simply be a different set of data etched onto a different two-dimensional surface. This transforms the multiverse from a collection of isolated bubbles into something resembling a vast cosmic data center, where each server rack holds the complete information for an entire reality. The most profound implication is that these holographic universes might not be entirely separate. Just as data can sometimes leak between poorly isolated servers, information could potentially transfer between these cosmic projections. The physics of one holographic reality might subtly influence another, perhaps through quantum entanglements linking their respective boundaries. A cosmic glitch in a neighboring universe could manifest as a strange, unexplainable anomaly in our own, a ripple in the fabric of our projected reality that defies all local explanation. We might one day detect these leaks not by looking out into space, but by deciphering the fundamental code of our own universe, searching for bits of information that do not belong, foreign data from a hologram next door. This suggests a multiverse that is not just a static collection of worlds, but a dynamic, complex network. These holographic realities could interact, influence, and perhaps even compete like living organisms in a cosmic ecosystem, all while we, living within the projection, perceive nothing but the solid, convincing illusion of our own solitary existence. Your own sense of an objective world, a reality you can point to and agree upon with others, might be a collective illusion. Quantum Darwinism tackles the deepest puzzle of quantum mechanics, how the fuzzy, probabilistic world of the tiny translates into the solid, definite world we all experience. It proposes that the universe itself performs a kind of natural selection on quantum possibilities, choosing which states survive to become our shared reality. This process is called environmental decoherence. Imagine a single quantum particle, like an electron, existing in a superposition, spinning both clockwise and counterclockwise at once. This fragile state cannot withstand the bustling world around it. The moment it interacts with its environment, with even a single stray photon or a passing air molecule, something profound happens. The superposition is disrupted. The countless possible states of the particle are exposed to the environment, which then selects for the most robust, stable states. These are the states that can be copied and spread throughout the environment most effectively. Think of it like a rumor spreading through a crowd. The most sensational, memorable version of the story is the one that gets repeated and becomes the accepted truth, while the more complex, nuanced versions are forgotten. In quantum terms, the environment acts as that crowd, constantly measuring the quantum system by interacting with it. The states that are best at creating multiple, redundant copies of themselves in the environment are the ones that win the competition. They achieve a status known as einselection, or environment-induced superselection. These einselected states are what we perceive as objective reality. The pointer on a dial pointing to a specific number, the cat in the box being definitively alive or dead, the chair you are sitting on having a definite position. These are all classical properties that have survived this quantum selection process. This means the solid world we all agree on is not the only possible world. It is simply the most stable and reproducible one. An infinite number of other quantum states existed as fleeting possibilities, other potential realities that were unstable and quickly erased by the constant interaction with their surroundings. They were real, but they failed to achieve objective status. This suggests a hidden multiverse of failed realities, ghost universes that flickered into existence for a fleeting instant before being wiped clean by the relentless process of decoherence. The universe we call home is not special because it is the only one. It is simply the one that was robust enough to be copied, broadcast, and ultimately perceived by us. Space and time feel like the ultimate, unchanging stage of reality. But what if that stage is an illusion built from something simpler? Emergent space-time theory proposes exactly that. It suggests that the four-dimensional fabric of our universe is not fundamental. Instead, it arises or emerges from a vast network of quantum components, like interconnected bits of information or entangled quantum bits. Think of a three-dimensional movie projected onto a flat screen. The depth, the movement, the sense of space you experience is not a property of the screen itself. It is an emergent phenomenon created by how light and data are organized. In the same way, the space between galaxies and the flow of time from past to future might be a magnificent projection from a deeper, more fundamental layer of reality that has no concept of space or time at all. This underlying layer is often described as a quantum network or a web of information. The connections between these quantum bits, their entanglement, create the geometry of space-time itself. Where the connections are dense and complex, we perceive the presence of matter and energy, warping space into what we feel as gravity. The passage of time might be the result of this network constantly updating, like a cosmic computer recalculating its state. If space-time is just one possible configuration of this quantum substrate, then other configurations are not just possible, they are inevitable. The multiverse in this view is not a collection of distant bubbles, but a vast landscape of different phases of this underlying quantum reality. One domain might have its quantum bits connected in a way that gives rise to a universe with 4 spatial dimensions. Another might have a network so tightly woven that time behaves like a spatial dimension, where you could walk forward and backward through moments as easily as you walk down a street. These other universes would not be far away in another dimension. They would be right here, woven from the same fundamental fabric, but existing as separate domains with different emergent properties, like ice and steam are different phases of the same water molecules. We are isolated in our particular phase, perceiving only the reality that our specific configuration of space-time allows. The search for a theory of quantum gravity is in essence the hunt for the rules of this underlying network. Finding them would not just explain our universe, it would open a window into the infinite variety of realities that could be built from the same quantum Lego set. Our perception of reality might be backwards. What if the universe does not create consciousness, but consciousness creates the universe? This is the radical proposition of biocentrism, a theory put forth by scientist Robert Lanza. It turns our standard scientific story completely on its head. Instead of life being a happy accident in a pre-existing cosmos, biocentrism places life and consciousness at the very center of existence as the fundamental ingredients from which reality is built. The laws of physics, the constants of nature, the very fabric of space-time, all of these emerge from the presence of a conscious observer. The universe is fine-tuned for life not by chance, but because life is the sculptor, the artist that brings it into being. This idea finds a strange resonance in the puzzles of quantum mechanics. Why does a particle exist in a blur of probabilities until a scientist measures it? Biocentrism suggests it is because the act of observation, the presence of a conscious mind, is what collapses those possibilities into a solid, tangible event. Without a living being to perceive it, the universe remains in a state of pure potential, an unformed symphony waiting for a listener. So what does this mean for the concept of hidden universes? If reality is dependent on a perceiver, then every form of consciousness could be generating its own unique cosmos. The world a bat experiences through its echolocation is fundamentally different from the world you see with your eyes. A bee perceiving ultraviolet patterns on a flower inhabits a reality alien to our own. In the biocentric view, these are not just different interpretations of the same objective world. They are, in a very real sense, separate universes, each brought into existence by the specific biological and conscious apparatus that perceives it. The hidden multiverse is not a landscape of distant bubbles or branching trees, but an infinite collection of private realities, each one valid and real for the consciousness that inhabits it. The solid, shared world we think we live in is then a kind of consensus, a Chinese letter of billions of individual perceptions that happen to agree on certain fundamental rules. But somewhere in the deep ocean, a whale's song may be shaping a cosmos of sound we can never visit. In a forest, the chemical language of trees might be weaving a universe of connection entirely hidden from our own. We are not just living in the universe. Each of us and every conscious being is holding a universe within us, and we are all constantly bringing them to life simply by looking, listening, and being. The profound question of why there is something rather than nothing has haunted philosophers for millennia. Yet, one of the most compelling answers from modern physics suggests that nothingness in its truest form is fundamentally unstable. Our entire cosmic story, from the first star to the last thought, might be the result of a single, random quantum hiccup. This is the theory of the universe from nothing, born from a quantum fluctuation in a perfect void. To understand this, we must redefine nothing. It is not an empty box. A true void, a perfect vacuum, is a state of zero particles, zero energy, and zero space. It is the absolute absence of anything, but the rules of quantum mechanics tell us that such a state is not serene. At the tiniest scales, the fabric of reality is constantly seething with temporary, spontaneous changes. Particle and antiparticle pairs flicker into existence for an unimaginably brief moment before annihilating each other, borrowing energy from the void and paying it back almost instantly. This is the quantum foam, a churning sea of potentiality. Now, imagine one of these fluctuations did not instantly reverse. Due to the bizarre rules of quantum probability, a bubble of space-time could have fluctuated into being, and instead of vanishing, it tunneled through an energy barrier into a stable, expanding state. Our universe was that bubble. It did not explode into a pre-existing void. The Big Bang was the rapid inflation of that stable fluctuation, the moment when the quantum loan was never called in and something came from nothing. The staggering implication is that if it happened once, it can happen again. An infinite number of times, the primordial void becomes a frothing cauldron of spontaneous genesis, where universes constantly pop into existence, each one a separate quantum fluctuation with its own random set of physical laws and constants. This creates a multiverse of unimaginable diversity, a cosmic lottery where every possible configuration of reality is drawn. Most of these universes would be stillborn. They might inflate for a fraction of a second and then collapse, or they might expand forever as barren, empty voids where forces are too weak to form atoms or too strong to allow anything but black holes. A universe where gravity is 1,000 times stronger might instantly crumple into a singularity. A cosmos without a nuclear force would be a thin soup of fundamental particles, never coalescing into stars or planets. In this vast ensemble of random worlds, a universe like ours, with its precise balance allowing for galaxies, chemistry, and life, is an astronomically rare winner. We are not the purpose of this grand mechanism. We are the incredibly fortunate byproduct of a random quantum event in an eternal, silent nothingness, living proof that even from absolute emptiness, everything can emerge. The smooth flow of time and space could be a grand illusion. Causal set theory proposes a radical alternative, suggesting that the universe is fundamentally pixelated, not just in space, but in the very essence of spacetime itself. At the most minute level, reality is not a continuous fabric. It is a vast collection of discrete, indivisible points. These are not points in space, but events in a network. What defines this network is not their location, but their relationship to one another, a structure of cause and effect. Each point represents a fundamental event, and the connections between them mark which events can influence others. This web of causality is the true foundation of reality, from which our familiar concepts of space and time later emerge. Imagine a sprawling, cosmic family tree. The individuals are the events, and the lines connecting them show who came from whom. The tree itself has no inherent sense of years or distance. Its structure is defined purely by these connections. In the same way, a causal set builds the geometry of our universe from the ground up, with the flow of time and the expanse of space being secondary properties that crystallize from this underlying network of causes. This leads to a profound vision of the multiverse. Our universe is simply one specific, incredibly complex arrangement of these causal set elements, but it is not the only possible arrangement. Just as you can shuffle a deck of cards into an astronomical number of different sequences, the same fundamental set of causal events could be rearranged into entirely different cosmic histories. Each permutation would constitute a separate universe with its own unique timeline, its own geography of galaxies, and its own laws of physics emerging from the new causal structure. These alternate realities would not be far away in another dimension. They would be different orderings of the same primordial ingredients, existing as part of a vast cosmic ensemble of possibilities. We are living in one specific story that can be told with this universal deck of cards, while an infinite number of other stories with different beginnings, middles, and ends are equally real in the silent landscape of pure causality. Every possible version of you is living a full and complete life right now. This is the startling claim of modal realism, a philosophical theory developed by David Lewis. He argued that our world is not special. It is simply one among an infinite number of equally real worlds. These are not parallel dimensions in a science fiction sense. They are entire, self-contained universes, each one spatio-temporally isolated from all the others. This means there is no path through space or time that can connect them. No spaceship, no matter how advanced, could ever reach these other worlds because they are not located anywhere in our cosmic landscape. They simply are. In this view, every single possibility is actualized somewhere. There is a world where you never left your hometown and another where you are an astronaut walking on Mars. There is a world where dinosaurs never went extinct and another where the very laws of logic are different from our own. When we say something is possible, we are not just imagining a fiction. We are actually referring to a concrete, physical reality that exists in its own right. The only thing that makes our world the actual world is the simple fact that we are in it. For the versions of you living in those other worlds, their world is the actual one, and ours is the mere possibility. This idea forces us to confront the very meaning of reality. We tend to think of the real as what we can touch and see, but Lewis suggests that reality is far grander, encompassing every single coherent story that can be told. The hidden nature of these worlds is absolute. There is no cosmic vibration or gravitational leak because there is no physical connection whatsoever. They are isolated by the very definition of their existence. This means the multiverse is not a single, connected entity, but a vast and silent collection of individual realities, each one a complete and closed book of existence, forever unread by any eyes but its own. The cosmos might not be a cold machine, but a learning mind. A new and audacious hypothesis suggests that the universe, at its most fundamental scale, is a neural network. This is not a simple metaphor. It proposes that the very dynamics of particles and fields, the forces that govern everything from stars to cells, are not fixed laws but the emergent results of an ongoing cosmic learning process. In this view, reality is not programmed with a set of rigid rules. It is a vast computational system that is constantly adjusting its connections, learning from experience, and evolving over time. Think of a simple artificial neural network designed to recognize images. It starts with random connections between its digital neurons. As it is shown thousands of pictures of cats, it strengthens the connections that lead to a correct identification and weakens those that do not. The network learns what a cat is. Now, scale this idea up to a cosmic level. The fundamental units of spacetime could be acting like neurons, and their interactions could be the weighted connections. The laws of physics we observe, like gravity and electromagnetism, would not be pre-written commands. They would be the stable, learned habits of this cosmic network after processing an unimaginable amount of data across billions of years. This learned stability is why physics appears so consistent and predictable to us. We are living inside a system that has already undergone extensive training. This leads to a breathtaking vision of a hidden multiverse. If our universe is one specific neural network architecture that has settled into a stable state, then other universes could be entirely different architectures. Some might be simple networks that never learn to form complex structures, resulting in barren, empty realities. Others could be wildly overcomplex systems, producing universes of chaotic and ever-changing physical laws. Our cosmos, with its precise constants allowing for galaxies and life, might represent a particularly successful and balanced model. Furthermore, these cosmic networks could exist at different stages of training. A young, untrained universe might be a place of extreme volatility, where the strength of gravity fluctuates wildly and particles blink in and out of existence without cause. We could be living in a mature, well-trained universe, while right next door, in a dimension we cannot perceive, a sibling cosmos is still in its turbulent early learning phase. This transforms the multiverse into a vast academy of minds, a multiverse of minds where each reality is a distinct consciousness at a different stage of its education. The solidity of your body and the certainty of the ground beneath your feet are the outputs of a cosmic intelligence that has learned to be stable, predictable, and ultimately habitable. We are not just living in the universe, we are the temporary expressions of its ancient, ongoing process of learning to be. The arrow of time feels absolute, an unstoppable river flowing from a definite past into an uncertain future. But what if this flow is an illusion, a mere current in a much larger ocean where cause and effect can run in both directions? This is the startling premise of retrocausality, a theory proposing that the future can reach back and influence the past. In such a universe, our cherished notion of a linear timeline would be a local oddity, not a cosmic rule. The implications rewrite our understanding of reality itself. Consider a simple experiment where a scientist decides to measure or not measure a quantum particle. In a retrocausal framework, that future decision could ripple backwards in time, affecting how the particle behaved in the past. The particle state is not just uncertain until observed, it is literally shaped by the observation that is yet to come. This is not magic, it is a potential feature of a universe where time is not a one-way street. The hidden universe here is a layer of reality where our past is constantly being subtly negotiated with our future, a cosmic dialogue across time that we are normally deaf to. Why does our world appear so resolutely linear then? It could be a matter of perspective and scale. We are macroscopic beings, and our consciousness may be wired to perceive time in a single, consistent direction. This creates the stable, classical world we need to survive. But at the quantum level, the true, time-symmetric nature of the cosmos might be on full display. This leads to a breathtaking vision for the multiverse. If our universe operates with a strong, forward-pointing arrow of time, other realities could be structured entirely differently. One cosmos might have a time arrow pointing in the opposite direction, where beings are born from their graves and live backwards toward their cradles. Another might exist in a state of temporal equilibrium, where cause and effect are a tangled web without beginning or end. In such a place, every event would be both the cause and the effect of every other event, a perfectly self-created reality. Our linear experience would be just one possible configuration of time in an infinite ensemble, a single, straight path through a forest of endlessly branching and looping temporal roads. The choices you make today might not just be shaping your future, they could be echoing backwards, quietly sculpting the very past that led you to this moment. This final theory gathers every hidden universe we have explored and places them inside a single, ultimate cabinet of curiosities. It is the level 4 multiverse, the ultimate ensemble of all that is mathematically possible. Proposed by physicist Max Tegmark, this idea presents the most absolute and all-encompassing form of reality imaginable. It states that every single mathematical structure that is free from internal contradiction is not just a description of a universe, but is a universe. Our cosmos, with its specific laws of physics, is not special. It is merely one particular, incredibly complex mathematical object, one equation in an infinite and non-denumerable library. The force of gravity, the speed of light, the number of spatial dimensions, these are not fundamental truths. They are simply the fixed parameters of the specific mathematical structure we happen to inhabit. In this ultimate multiverse, there is a reality for every possible variation. There is a universe where space has 42 dimensions. There is a cosmos where time is two-dimensional, allowing for a plane of moments instead of a single line. There are worlds governed by the simple geometry of a perfect tetrahedron, and others where the laws are so alien that concepts like matter and energy have no meaning at all. This theory does not just contain the bubble universes of cosmic inflation, the branching worlds of quantum mechanics, and the holographic projections. It subsumes them all. The Level 4 multiverse is the set of all sets, the reality that contains every possible self-consistent reality. The reason our universe appears so finely tuned for life is stripped of any mystery. It is a simple selection effect, an anthropic bias. We could only find ourselves asking these questions within one of the infinitesimally rare mathematical structures that allows for the emergence of conscious observers. We are not the purpose of the cosmos. We are a possible outcome that had to occur somewhere within the infinite sprawl of mathematical existence. This idea removes the need for a creator or a fundamental substance. The multiverse simply is because mathematics is. It is the ultimate hidden universe, not because it is far away, but because it is built from a substance more fundamental than space or time, the silent, eternal language of logic itself. Every story that can be written with that language is being told in a cosmos of its own, a final, breathtaking affirmation that reality is far grander, stranger, and more wonderful than we ever dreamed. We have journeyed through 30 windows into the unknown, from the quantum splitting of your own consciousness to the cosmic birth of universes within black holes. Each theory, from the holographic principle to the simulation hypothesis, paints a different facet of the same staggering possibility. Our reality is not a solitary island, but likely one thread in an infinite tapestry of existence. While these ideas remain at the frontier of science, not proven facts, they stretch the very limits of what we can conceive, merging physics with philosophy in a quest for ultimate truth. So the next time you find yourself under a clear night sky, look up at those points of light. Remember that what you see is only the surface. Beyond the stars, beyond the dark, an entire cosmos of hidden worlds may be hovering just out of sight, a silent, bustling multiverse waiting for us to finally understand. Which of these possibilities captures your imagination the most? Let us know your favorite theory in the comments below. Your journey into the hidden layers of reality does not have to end here. This newfound curiosity can be the first step toward a lifelong exploration of the cosmos. To dive deeper, begin with the books that have shaped modern thought on these topics. Brian Greene's The Hidden Reality offers a masterful tour of the multiverse, while Max Tegmark's Our Mathematical Universe presents the staggering case for a reality built entirely from math. For a crystal-clear guide to quantum mechanics and the nature of time, Sean Carroll's Something Deeply Hidden is an essential read. Beyond books, immerse yourself in documentaries from PBS Space-Time or the BBC's Horizon series, which visualize these complex ideas with stunning clarity. For your daily commute, podcasts like Sean Carroll's Mindscape or Star Talk with Neil deGrasse Tyson break down the latest cosmic discoveries in engaging, accessible conversations. If you are ready to truly challenge yourself, explore the free online course catalogs from institutions like MIT OpenCourseWare, where you can find full university lectures on cosmology and particle physics. To stay at the very frontier of these ideas, follow the public outreach from research centers like the Perimeter Institute for Theoretical Physics, which regularly publishes articles and videos explaining breakthroughs as they happen. The greatest mysteries of existence are still being unraveled, and by engaging with the work of these scientists and educators, you become part of that grand conversation. Let this be the start of your own voyage into the unknown.